Okay. All right. Who wants to learn now for another hour? Learn more things.
Are we gonna learn how to
just redo the
Dabble?
entire week. Like,
I mean,
restart it.
so I mean, there's it might be worthwhile, but I'm happy to go over like any of the topics. Bring them up at office hours. I think we'll do office hours again at on Sunday if everybody likes that time. And like really bring me like questions about the things that you're having trouble with. And we can review them. And really, I mean, anytime messaging the moderators or the what do you call it, instructors and Will and
That'd be like one-on-one time.
absolutely, yeah. Scheduling that is a great idea, and I think that Alice, that idea to have people do pairing is a terrific one, and I really think I hope we'll get some time to do
I
that.
was gonna say, if I know I have this Slack, I'm definitely free, but I'm just saying in general, like we're all on Slack all the time, so definitely hit us up. I know Max he uses Calendly a lot within Slack, so definitely like even like if Jesse or I are here, everyone's here.
Is that something we can join, Calendly? Or?
Yeah, so Calendly is it's just like a meetings sort of like maker. Basically, he just posts it syncs with group calendar, so it'll tell when you're available.
Oh, cool.
You can schedule stuff based on availability. A lot of startups do that. We had this meeting with this woman coming out of San Francisco a couple days ago. She just like, you're like Calendly, sign up. Okay. So yeah, definitely you can take advantage of that. But Slack works.
Cool. I'll look into that. But yeah, we should definitely. I mean, a lot of this stuff is, stuff that is. This is Jesse and Jeremy were at the other door, and it doesn't open, so they were locked out.
I don't know the dog. Is that a dog?
This is a raccoon or a red panda.
It looks like a trash panda, so.
Yeah.
It's a red panda.
Yeah, which is basically a raccoon, right? I mean, they're like.
But they're much cuter. And they're from Asia.
That's subjective. I think Asian people might think that raccoons are cuter if they don't have,
You're right.
Just saying.
It's always what we can't have.
Yeah, the grass is always greener. The panda is always cuter, All right. Anyway, so yeah, message people, and let's continue this conversation in the several weeks to come about doing pairing on stuff. I assume a lot of you are going to want to get some sessions going for when you're actually starting to set up your, whatever servers and infrastructure in your projects for your capstones. I think a lot of people are getting to the point where, you can start actually building out building out the pieces that you're going to use. Definitely talk to Max next week because he's going to be going much deeper into building servers, the whole, and he'll be integrating the whole thing. He's going to be using data and databases and doing things like user accounts and pieces that you're going to definitely want to be adding. So there's plenty more of that coming up, and I think this is really the point where I wouldn't be surprised if you probably right now are staring at this capstone idea and you're like, this is where we start to implement things, and it's just very it's daunting because it's a big project. But I think I recommend starting with the data model, starting with an API, but also starting with sketching the interfaces that you want. And Karen's actually got this awesome note paper and has made some really cool, like pencil and paper sketches as the first way to get the interface. And now, of course, you've started trying to use Bootstrap to make them and run smack into that wall. So that's fun, but starting to approach it from both of those sides is really the next step. Is really what you're going to have to do.
One page of my project took me all week.
Yeah.
To finally get it to look like that. Stupid Bootstrap. That's awesome.
Well, that's pretty good.
That's great.
That looks really good.
So you want, you know, I mean, I don't know. I mean, that's a long time to spend on it, but that does look very good. All right, anyway, yeah, so you know, I'm definitely, like, you know, I'm not gonna be teaching next week, but I'll be in the Slack and we will be talking about the one-on-ones. Max will be hosting his one-on-ones as usual, and there's gonna be a whole lot more on servers and data right up ahead next week. But today, we're just gonna go through a whole bunch of other topics that are related. They're data stuff. They're not data stuff you might run into. A lot of today is not relevant for your capstone, pretty much. You're not going to need this. This is information. This is background. This is like learnings and things so that you are, you know, have some basis for like understanding and talking about these things. If you run into them down the line, if in a couple of years you're working on a team that uses key value databases, the only exception is Mongo. Like you might just want to use Mongo for your whole capstone, which is a different database than Postgres. It has different strengths and weaknesses, and it's a lot, you know, in a lot of ways it's going to be easier to use, and I think Max is going to be both using, you know, demonstrations with Mongo and with Postgres. So like Postgres and SQL and all of that stuff, it's sort of, once you start having a lot of concepts and related data that relates to data, it's pretty much the standard for that. You'll find that in just about any job you're working. But for a prototype and for a lot of other kinds of like things that you want to just, you know, get working and to be easy to use, Mongo is a good choice. So you might consider that as well. Okay. So we're going to talk about other data stuff. The first thing is indexes. I think we looked a little bit at, or I mentioned very briefly what an index was in the database. I think everybody kind of already knows what an index is. You've all seen them in like a textbook or a encyclopedia, or, you know, I don't know if is there like a book around here that would have an index in it? There's probably one over there. But you know what an index is. It's the part at the end of the book, and there's like a whole bunch of alphabetical list of words, and it's like, you know, your car manual has one. It's like you go to S and you find seatbelts, and it says seatbelts page 200, and you go find the seatbelts. This is the PHP cookbook. And here's the index. So it has numbers, accept encoding header, add advisory file locking, anonymous binds. So you know what you're looking for, the word or the value or the thing you're looking for. And the index is a collection of data, which basically has a bunch of locations. It's got the word or the value or whatever it is, and then the place to go find it. And it's the exact same thing in the database. It's a collection. It's a thing that you build, which is just a whole list of values and where to go to find them. So just like in a book, building the index is not like a trivial, it's not easy to do. Building the index in one of these books is a large task. If anybody knows editors or that process, like you have to do it when you know all the pages for everything. So you have to do it after you do all your typesetting and your pictures and everything. You know what pages things are going to be on. And then you have to build the index to have all of the terms that you need. It's the same kind of idea in a database. It's more work for the database to do when you're writing the data. So you're really effectively trading some work when you're writing data into your database to build a special structure, a special thing, which is then going to allow the database to go look up that same data later. And it's going to be able to look it up faster and to do your queries much faster than they would otherwise in some cases. So you're trading some extra work when you're adding data for a much easier time when you're going to read that data back or look for that data. Okay, so I mean, more specifically, when you do like a select star from the table or select a column from a table where something equals something, or join with a table on something equals something, the database is going to have to go through into those tables, and it's going to be looking for columns that have the values that you're trying to compare, right? It needs to find matching values for your where clause, or it needs to find values in one table and match them with the values in the other table so it can join them together. So if you have the right columns indexed, so when you do where something, if you have that column indexed, the queries will just automatically run a whole lot faster because the database is going to see, it knows what indexes there are and everything. And then when it's building a plan for what it's actually trying to do, it's going to see that, oh, there's an index on what I'm trying to compare here. So rather than go directly to the table and read through all of the data in the table, I'm going to go to the index and I'm going to quickly look up. It's designed for quickly looking up, where the certain value is, and then it will point me right to the places in the table where that data is, so I don't have to go scan through that whole table. If you have the right kind of index, it's an ordered index. So just like the book index is alphabetical, there are indexes where the database can very quickly, you say, well, I want every user with a birthday between 1960 and 1970, and it's going to know from looking at the index where to go. So it'll say, the index starts here, here's 1960, here's 1970 in the index, and basically everything between that and the index is going to be between 1960 and 1970. And so it can find that range very easily too. But again, like if you're ordering by, or if you're selecting where a certain thing is true, or you're looking at a certain column that's not in any index, or sometimes if you're looking where two columns are true and the first column is in the index, well, maybe it'll use the first column to narrow it down a little bit, but then when it gets to the second column, it's not going to be able to narrow it down anymore. And if they're reversed, sometimes it just won't be able to narrow it down at all. So if you don't have the right values that you're filtering on in your index, it's just not going to be able to do it. And this doesn't mean it will break or it won't work, but it means that once your database starts having like hundreds of thousands of rows and millions of rows, then it will run very much noticeably slower to get the same query. So this will be something where, a database administrator, if you have someone you're working with, a lot of their job is going to be understanding the indexes that are in the database. Which ones are worth writing when you write the data? How many indexes can you afford to write along with your data because you're writing so many rows every day or whatever? And which ones are going to help you with the queries that are taking the longest? So really looking into that and planning for that is a large part of a database administrator's job. Okay, let's look at just how some of these indexes work. The first kind of index and sort of the standard is called a Btree Index. It stands for Balanced Search Tree. And it's basically like the normal index. Whenever you say just create index in Postgres or whatever, and you don't tell it which type of index, it's going to make one of these. And these are really good general purpose index. When you're trying to find a particular value, it has really good performance. It can find that value in 1 or 2 or 3 or 4 hops, even for a very big table. And that sort of means it looks in one place and then goes to a second and a third, and then it finds it, rather than scanning through a million records. It has very good performance also when sorting. So you can find a range, or you can say, I want everything in order of this value. And the Btree is ordered. It actually it stores the data in a particular order, so that it's very good at scanning back and forth when you're ordering by a certain value.
Yes.
Yeah.
So I'm just trying to picture what I'm using this for. So when you go to like a doctor phone anywhere, and they're pulling up your records by your phone number or your last name, is that the kind of thing that it's using, an index?
When you go to
Oh, anywhere, like, they're pulling up your.
I mean,
records.
it doesn't necessarily have to, like in most of those cases, unless they have millions and millions of records, the time it takes to type in your name would be longer probably than what the database takes to look through all the data in the entire database. So it's not really going to make much of a difference, but if you're, I mean, if it's like a huge database, if it's like a network of insurance or whatever, and they have millions of records and they're handling, many queries per second, and it's the same system and they want to handle many queries per second, then yes, you're gonna want to put an index in there, which will mean the database doesn't have to look in order through every piece of data that it has. When I say, oh, I use subscribe ID or whatever my number is, you put that in, it would have to go and check, is this it? Is this it? Is this it for everything until it finds it, right?
Okay.
But if it has the index, there's like a place where it knows that value to look for that value. Just like you look in the alphabetical order, you go to the letter that it starts with, you know where to look for it. So it knows where in the index to look for it. And then that entry in the index, because it's taken the time ahead of time when it wrote that data to make an entry in there, it's gonna have right there next to your number that you are asking for where to go find it. So it'll go right to the place in the database, in the table, actual data where that data is, and be able to pull that right out. Let's look at a little more of like how. So the Btree is like a little bit. It's sort of clever how it works. It doesn't just put a list of all the values in order and it scans through the list of values. It's actually much faster than that, because what it actually does is builds a tree structure. Like this is the trunk of the tree, and then sort of upside down, but those are the leaves of the tree. And what happens is when you say, okay, I'm looking for a number, I'm looking for number 5, right? It's going to say, first, always, look, when you're looking for 5, right? First, check this first top node. You always start here. Now, 13 is the number here in this level. But 5, and it'll compare, is 5 greater than or less than 13? So it needs to be able to sort. So you could sort alphabetically, or it could sort numbers, or sort on any other way you could think of sorting. But there has to be a greater than or less than concept. So it says, is 5 greater than or less than 13? Well, it's less than. So in between each value, you see these little tiny dots here. These are actually references or pointers to somewhere else. And in this case, you go down one level in the tree to where, well, less than 13 goes over to says, look here next, right? And then you do the same thing. You say, is 5 less than or greater than 7? Well, it's still less than 7. So you follow this one, the less than one, down to here. And then I think you just look through this whole thing. Is it one of these? And it's 5. And then this last row represents, like, here's where it says, okay, here's where the data for 5 is found. This whole process is to get to the actual place where you can find the match for 5. But this might point to a whole row of data that's for person number 5 or whatever.
So it's like essentially instead of reading through a whole crap ton of stuff, it's like just saying true or false and like move on.
Right, and it's doing it 3 times in this case, as opposed to, like, let's say you have 37, it's 3 times, as opposed to nope.
Right.
Or looking through every row. Like, even worse, with no index, it would have to skip along every row and say, check the value in every row. So this is much more efficient, as you can see, when you're looking for a certain kind of data. And it's like 3 or so lookups, and there's more and more as you have more and more. If there's millions of rows or whatever, there's a whole scheme of like when you break things up into leaves and when you add layers underneath and everything. So there could be 6, 7, 8 layers, but it's still going to be much faster than any other way to like scan through it, except the one we're going to look at in just a bit. But the other thing about this is that, let's say I want everybody between like 13 and 37. All you have to do is start and look for each boundary. So you look like 13, well, I guess equals is this one, whatever. Because 13 is down here. So equals is considered the same as greater than, I suppose. It goes to here, okay, less than all of these, so it goes over here, found 13. Now look for 37, greater than, it's here. It knows where it's starting and where it's trying to end up, and all it has to do is scan along here. And actually, in this case, I don't know why there's no arrow here, but there will commonly be a way for it to skip along. But each one is in order, and they go right along from in the exact range you're looking for. So you can not only like find one value pretty darn quickly with 3 hops or something, but you can also order by. You can also find where every row is by the order of this particular value, or you can find, pull back a range, something between a value and another value very, very easily. So this is why it's sort of a standard, because it's very general purpose. It's good. It's very good for all kinds of common lookups. Okay, the other type we'll talk about, and there's like more types. There's actually an index that's optimized for geospatial like coordinates, like maps and things. There's all kinds of like other schemes that people have come up with for like putting data in places that are easy for the computer to find. But these are the two kind of important ones. The ones you'll see. This one, you'll see it, or it shows up places, but you're probably never going to actually have to use it manually. You might use something that makes use of this, but you don't usually tell Postgres to use a hash index because we need to talk about what hashing is, and this is sort of like what Bitcoin does and all of that. In one of the parts of Bitcoin uses the exact same concept. A hash index uses a hash function. Oh, I skipped this slide. Hash index uses a hashing function to determine the in-memory location for each value. So it puts, instead of saying like go through this tree and compare greater than, less than, and greater than, less than, it basically says take the value you're looking for, shovel it into a special function, and what will come out of that function is the hash of that value. And if we look at, just lost, is someone have a noise in the background? Elizabeth, I'm going to mute you if that's okay. Holler in the channel if you need to. All right. Okay, so where did my presentation go? It's gone. Okay, let's just really quick look at this hash function link. Okay, a hash function is any function that can be used to map data of arbitrary size onto data of a fixed size. So you put it in the number 5, or the word blue, or the entire text of Moby Dick into a hashing function, and it will give you back a string that's about this long, or however long you want. Your function determines how long the string is. And that string is long enough so that unless you put the text of Moby Dick in again, you're not going to see the same one again. So 5 will have a unique long string. Blue will, red will. If you put blue in again, you'll get the same one for blue, but it's very long, and it doesn't really correspond to anything, And again, you can put as big of a value as you want, and you'll get the exact same format output, right? So this basically lets you take the values that are in your database, no matter what they are, and translate them into some kind of output, which is arbitrary, but it's predictable, and you can map that to different memory locations and buckets for where your data is. And it's the same kind of thing. You get your hash out. That tells you where to go look. It's one lookup or two lookups. You find a bucket, and then you look through the bucket, usually, right? But it's only good for looking up one value at a time, okay? So a good hash function will produce those outputs, and they will have very little to do with what you put in. It will be very hard to predict what comes out for any given value, and they'll be evenly spaced throughout. So if your hash is like, let's say, a number that's like between 1 and 10 billion, real hashes are much, much bigger than that. But let's say your hash is a number between 1 and 10 billion, right? You put in blue, you'll get any random number in between 1 and 10 billion. You put in the text of Moby Dick, you'll get another random number in between 1 and 10 billion. You never really know where in that space you're going to get it, the output, until you actually do it. And they use what's called a trapdoor function mathematically to make it so that you can easily check what the text of Moby Dick, or fairly easily, or a number or a word translates to. But if you give the person the hash that blue or whatever translates to, there's really no way to undo that, right? There's no way to say, oh, I know all of these bits. This is what blue was. You have to try blue. You have to try every color. You have to try every string of every word. You have to try every book or every possible book in order to find the hash, right? And this is sort of what Doug was talking about when people mine Bitcoins, right? How do you prove that a computer did a whole lot of stuff? Well, it tried all kinds of different values until it got a hash. This is actually how it works. Until it got back a hash that everybody agrees is special enough to win the block. That's how it works. So like if the beginning of the hash starts with so many zeros, sometimes you got a lucky hash or whatever it is, and that's how you mine the block. So they're used for all kinds of stuff. Max, next week or in 2 weeks, he's going to show you how you use them for storing passwords. The whole idea is you can't get the password back out of the hash. You can check that the hash matches by putting the password back into the hash. You can't get it back out. Anyway, we're not going to go into any of that today. This is just kind of an aside. Hashes are very cool. They're used all over the place. But in this case, they're just used to turn it into some kind of arbitrary value that's arbitrarily randomly spaced amongst all the possible hashes. And then it gives you a place to go look for your data, and that's where your data will be stored. So they're very good for like trying any one value and finding where that value is. Put it into the hash function, try that. They're not going to be good for orders or range queries because, again, blue is one random hash. Blue, BLEU, would be another totally random hash. So there's no way, like in the order, the things that are close together, number 5, number 6, number 7, are all going to have totally random outputs, and they're going to be all over the place. So there's really no good way to say, I want all of the hashes for the values between 5 and 10, or the dictionary words, or alphabetical order. Any kind of ordering is not going to work well with hashes. Hard drives put close together data, and data that's closer together is faster to look up sometimes than data that's farther apart. So like in most ways that you access data with the patterns, like unless you're really always looking for a single random value one at a time that's totally random, and it could be anywhere, and you really want to avoid the 3 hops to go through the Btree, or the 4 hops or whatever, that's when you might want to hash. But in all other cases, there's really no benefit to it at all. So Postgres has the option, but I think even their documentation says, like, you don't need to do this. Like, and you pretty much don't ever need to say that you want a hash index in a modern database. But that's what it is, and it makes use of hashes, which are all over the place. Here's a picture, sort of how it works. This red or pink sort of band here is the hash function. So let's say, okay, the names go in here, And either you're, I don't know if you're hashing the ID or the name or both, it doesn't really matter, as long as it's consistent. And the hash function, see, each arrow just goes to kind of a random place in the output range, right? The output is 000 to 255. And each one sort of ends up randomly being shuffled somewhere predictably. So it's always going to go to the same place. The same value goes to the same place, but not in a way that, like, where the pattern of the outputs makes any sense. They're all over the place. But then these outputs each are small buckets, which have the pointers to the actual data. So there's basically two hops. Into the hash function, check the bucket, the one bucket where it tells you that value can be found, and then follow it through to the row. That's a hash index. Okay. So those are fun, right? You don't need to know any of this for your capstone. You're not going to need to set up an index. You'd have to spend a long time generating enough test data to make your database slow enough where you could even notice an index. But we can try it out if you want to see.
Do you guys use indexes at work?
All the time, yeah. There's, you know, spending a day on indexes. I don't do it lately, but there was like a couple months, a couple years ago, where I was actually looking at indexes and trying different indexes for probably a week straight, because it, you know, there's certain things which you're doing so often, and you have so much, so over and over so many times that you're like, well, if I can, you know, if I can make this index just a little bit more efficient, the whole thing will get faster and it'll just stay faster. So it's worth it in some cases, yes.
Do you know, like, you guys have like user interface for like clients to see like all their data?
Yeah.
Is that where you would use that so that like
We use it in the database when we're processing that data. So if you want to say like how many people were in these buildings in the month of February, that could be like 300, 400,000 people traffic, you know, and you want that request to come back in very quickly. Well, what we're doing, I mean, we sort of do several possible approaches, but one of them is put the right indexes in the database so that it can find that range very easily and then efficiently retrieve those numbers. And then, you know, the next step after that, though, is to like pre-calculate what people are going to look up, like the daily statistics or whatever, and write those somewhere so that, you know, we don't have to look them up at all. You know, there's many strategies. So, yeah. But yeah, I mean, indexes are sort of like bread and butter of like big data or medium data to big data. You know, big data means like massive data that probably starts to not even fit in Postgres because it's just too big and you need 10 Postgreses all sort of talking to each other or something absurd like that. That's something I've actually never really seen is data that needs to be that big. Like my brother works on like financial stuff and it's like transactions and he's worked in like finance, and that's like digital trading, high frequency. It's like stock exchange. It processes so many billions. It's like they literally talk about millions per second of things going on. And that's like a totally different, so that's big data. That's like when data gets very big. And a lot of this stuff is like not even gonna help you out. But you know, everybody who does data doesn't do that. That's a very special case. That's like, you know, that's a very niche thing, and it's something that you would do as your career. You would just work with that huge amount of data as your entire career, you know. Okay. So, yeah, those are indexes. Let's, do you want to see sort of a demonstration of how to do an index or what an index is? We could set one up really quick in Postgres if you want to do that right now.
Yeah,
Okay.
that'd be good.
All right. Oh boy. Should I set this up? Okay. Well, cool. We've got Postgres. It's just still running. Select star from users. And we have only 3 rows in our database, so it would be completely absurd to build a index for these 3 rows, because it's sort of a waste of the computer. But how on earth do I get rid of this one? Yeah, all right. So even there, doesn't fit on 1 row. There we go. Okay. Huh. Come on. Full width. Nice. All right, so we have 3 users. There's no reason to ever have an index, but let's. I might have to look up the raw Postgres way of doing this, but I think it's create index. I think you give it a name, users index. And I'm going to look it up. All right, 9, 11 is close enough. It's all going to be the same. So you can say create index. Now you can say unique. And when you are in your ORM in Sequelize and you say this column is unique, true, it's going to make an index. That's one of the things it actually does to guarantee that it's unique, because a unique index is just another index, but it can take advantage of the fact that no 2 rows can have the same value. And it actually, that's what checks each value when you try to insert it to make sure there's nothing already there with the same value. So that's what a unique index is. But we're just going to say create index, and it will be name on table name, and then parentheses column names. I think that's it. Okay. And we don't have to say Btree or whatever it is, but you can say, no, I want this index to be a different kind of index. Create index here. Sorry, it's on. Yeah. I was really close. Users. And then you do parentheses. And let's say this is an index on birthday. Okay, so it says create index. Now we have an index. Okay, what did that do? Well, not much. I mean, you can still do for our table, there's really no point again. You can still do select from users where birthday is greater than 1998. And this will only return 1 row because this one is 1998, January 1st. So it still works exactly the same. It doesn't affect how you use it or like what Postgres will actually do, but it's going to run faster in most cases. It's not going to matter right now, but it's going to run faster. And you can actually see why. You can run a special command in Postgres called explain analyze. And then you put the whole rest of your query that you just ran. And this will actually ask Postgres not for the data, but it will say, hey, Postgres, tell me what you're going to do to go fetch that data. And it will list out all of the steps that it will take and how long they take in order to do that. So select star from users where birthday is greater than. Okay, so this is the query plan. See, it gives you 1 column back. The column is called query plan. And this isn't your data. This is what Postgres is planning to do in order to fetch the data. So it says sequential scan on users. That's not right. Rows removed by filter. Maybe it didn't even bother to use our index. Why didn't it use the index? So this is what you don't want to see. When you're using an index, you want to see index scan. Because this means it's going to go through every row in your table and look for whether the birthday works or not. But it's possible Postgres is very clever, and it's like, there's only 3 rows in this table. Like, let's not bother. So my demo is going to fail here. That's not right. Let's try where ID equals 1 and see what it says. Yeah. 10. It's not using the indexes at all, not for ID, not for anything. I think it might be because there is only 3 users. We could, you know, I'm going to poke in, dig into this, but it should say index scan if you have the index, and then if you delete it, this is what it will say on a big table if it's taken a long time and you do explain analyze. I think this means, unless I'm just, forgetting here, index scan versus bitmap scan versus sequential scan. So sometimes when some of the columns, if you're trying to filter or order by several columns and some of them are in an index, it'll do what's called a bitmap scan, which is like using as much of the index as it can. So this is some Btree stuff. Bitmap scan. Yeah, this is index only scan. This is what you want to see when you're using your indexes. Index only scan. That means all it looked at was the index for these values. But I think it's probably because we only have 3 rows, and it's not even bothering to use the index. So bit of a bummer. The demo didn't work, but it would. That's how it works. Okay. So next, let's take a look at some key value databases. So these are different kinds of databases. This is not Postgres. Key value databases match a huge number, potentially, of unique keys to values that you set for each of those keys. So your example keys could be a big number like this. This is actually in density. This is the number of, I think, our Syracuse office room. This is the ID. And this could be a key in a key value store. Or you could say like a longer thing, person, this, edit this, if you're saving some actions that people take or whatever you wanted to save, as long as the key is unique, it can be, I don't know if there's a limit length in most of these, but it just has to be a unique something, usually a string or a number that is the reference that you're going to use to store a certain value. The value could be a lot of text, it could be another number, it could be a hyperlink, it could be a book or whatever. Okay, so a pretty famous key value database is called Redis. This is used a lot everywhere. I mean, we use this, and it's sort of just a very good, solid, very fast key value store. You give it a key and a value, it stores the value. You say what value is at this key, it gives you back the value. And it's just strings. I think it's like all flat strings, and it has like numbers, but I think everything's probably just a string. Anyway, we can try it out really easily now that everybody has Docker. If you want to run these in your terminal, and you should be able to do this from anywhere, we can try a little bit if you're interested. So you do VS Code, quit Postgres, exit that Docker. So I think I already ran this one. Docker stop Redis. Okay, so you can do Docker pull Redis, and this will download the latest Redis container. Docker runs any of these things, and image is up to date. I already did it. And then you can do Docker run -d, that means in the background, --rm, that means remove it when it's finished running. The name is Redis. The Redis port is 6379, so you map that port to the outside of the container. And then what you want to run, which is what we just pulled. which is Redis. So if we run this, we have Redis running Docker PS. We can see we have the Redis container. And in order to interact with it from JavaScript, you can npm install Redis. It's all pretty straightforward. And I'm in this folder, so whatever. You might want to be in a folder where your project is or whatever to do the npm step, but as long as you, what's up?
So I'm just curious, why would you pick this type of index?
This is not an index. This is a whole different database. So you pick this because it's very fast.
Okay.
It's very efficient, and you can sort of scale this horizontally. If you just need to store millions or billions of like some values and just work with them as fast as possible, Postgres is pretty darn good at that. Like, it's pretty darn good at almost everything, but it's like a big system and everything. And also Redis is what's called single-threaded. So there's no, it only answers one query at a time. It does everything in sequence. And if in certain cases, when you're doing a whole lot of very lightweight operations, you don't want them to conflict with one another. And in Postgres, like if certain connections are waiting for other connections, they'll all try to write to the same place, and Postgres will sort of get bogged down or even deadlocked. It'll be like one thing's trying to write the other thing, and another thing's trying to write that first thing. And neither one will ever finish because it gets stuck in it. And so if you're doing a whole ton of writes, and you want them, each one to be as fast as possible, each Redis instance is going to write incredibly fast, and it's going to write one thing at a time only. So it's very, very, very good at that. A very large scale, a lot of writes, one thing at a time. And then you can also, once you get too big for a single Redis, you can there's ways to cluster them together, and you can rent the whole thing from Amazon. So you can do AWS. They have a thing called Elasticache, which is just like, give me a bunch of Redises, and they run them for you, and all you have to do is connect to them. So in production, you don't need to run it yourself or anything, and it just sort of scales up to whatever you need for storing a whole bunch of stuff. And I'm sure there's like pitfalls and problems at certain scale, but that's what it's for. It's for a large, fast amount of writing a bunch of small, quick data.
Can you give us an example of what you would do that?
Yeah, so one thing we're using it for is one thing we use it for is we have all these devices, and they upload statistics, right? And we have like a cache sort of current latest state of everything, 10, 9, 10 people, 11 people. It sort of, that's one value which sort of gets updated. Rather than writing new data every time, we're updating a value. So what happens is, let's say there's like a whole building with like a lot of stuff, there's a whole building with a lot of these things in them, and it's been running for a day or something, and its internet went down, right? So what happens is we don't, like, the system doesn't stop working, but they can't upload anything up to our cloud, so they keep retrying. And then let's say they turn the internet back on, and all of a sudden there's 100 devices that all have 1,000 backlog of events, and they all say, we want to upload these as fast as possible. Well, that's, we have a pipeline so that we can sort of process through them very quickly and write in each new record. That's no problem. But if we want to say, okay, there was 10, 11, 10, 12, the order of them coming in is going to be all over the place, and the devices are going to be all trying to write at the same time. So at some point, like, it just becomes very slow to try to say, okay, this person's updating the row now. Okay, everybody else is locked and waiting, and there's connections sitting open. Now this person gets the lock, and it's very inefficient at doing that. So what we actually write those values into Redis, because then you can just say, here's 10,000 requests real quick, and Redis just churns right through them one at a time really fast. So it's very good at that. Okay, but anyway, we have it in NPM. We can do node. I have a cheat sheet here with my code. You can do const Redis equals require the string Redis. and then you do const client equals redis dot create client. And the defaults here are localhost, which is my computer, and 6379, which, as you can see, our Docker is mapped. That port will get through to our Docker that we just started. So we don't have to give it any options. The defaults will work. And then we can say now client.set. The first thing here is the key, and the second thing is the value. And this could be just any string, anything you want. I don't know what this third thing is, but it was in the example. So I guess this tells it to print the reply or something. So it says true, it returns true, and then we get reply OK. That means it wrote the key. So if we try to get the test key, now this all works with like callbacks. It's all asynchronous, like almost everything with Node. So it doesn't, you have to give it the function to run. And if you want to use this with promises and async, you have to like set it up to work with promises and async and all of that. So it's a little bit of setup, but I mean, it's pretty much that easy that you can log this is the error and the value that come back out for this key. You see we got my test value back. And whoop-de-doo, you can do that with a variable or whatever, but you can do this with millions of things very, very, very fast. And all, for many clients all at the same time, and collect them in one Redis like that. So it's very good at just writing and loading values for all kinds of different unique keys. Okay, that's pretty much it. It does some other things. We'll dabble. We'll just look at one or two other things Redis does, but that's really what its core component. That's pretty much it. And I think it uses a hash. It's all like hash based. So it's, as far as I know, like you can't really do range queries on keys very easily, or at least when I search for it, it's like nobody does that. I think it's for writing one thing at a time, and I think therefore it's probably using hashes to know where to put everything. I think. Okay, so document databases. This is a slightly different kind of database. This is very similar to a key value database, but it's a special kind. The values aren't just strings. They're actually like full-on JavaScript objects, basically. They call it BSON, which is like binary JavaScript. So it just means they're faster than just JavaScript. It's another very fast database, but you can write JavaScript objects in and read, and you get the same JavaScript objects out. And you can actually do things like index parts of the JavaScript object. So you can do all kinds of things that allow you to go beyond just looking up a single key at a time. The standard, the one that everybody uses is MongoDB. You've probably heard about MongoDB. It's very much like a companion to like Node and JavaScript because it's sort of native. It stores the data in basically the same format. It's very easy to like read and write. If you want to try Mongo, it's very similar. You do docker pull, click this, docker pull Mongo. And I already have it, and I think it's already running, so I'll stop it. And then you do the second thing, which is run in the background, remove it when you're done, name is Mongo. This is Mongo's standard port, which is 27017, and then Mongo. And that's it. So I think there's an npm Mongo package that's very similar to the Redis one you get and you set, but what you get back is like a JavaScript looking type of thing. But we'll do npm install mongoose, which I think Max might be using next week or the week following, at least one. And this is sort of basically what I would say is a sort of full-on alternative for your capstones. Maybe the one thing today that you might consider trying for prototyping or for your whole capstone would be using this thing instead of SQLize in a SQL database. Very similar concept. It would be where you store your data. You still want to model your data. You still want to figure out the right structures for it. But this is a way to put it into a Mongo database instead. In order to use, I have my cheat sheet here, which I will refer to again. So in order to use Mongoose, you do const mongoose equals require mongoose. And mongoose.connect, and you give it this MongoDB URL here, and you tell it localhost 27017, and then /test, I think it can be anything you want there, but that's like your namespace or your table or whatever it is. There's a slash, and then this will have the same kind of purpose as a table, I think, in a relational database. And it's very free form. Like, it doesn't care that there's no such thing as test yet. It's just like, now you're in test. Everything you write will go into test. And then whenever you look into test, that's where your data will be. So it's very, very, very less constrained. And therefore, it's going to be quicker to get started and to try and to use and everything. But the flip side, of course, is that it doesn't really guarantee much, if of anything, about your data. So once you're writing your data and you're in production, you know, some of your data could be in different formats than other data, and the database is not really going to catch on nearly as effectively as it would with some kind of SQL. So that's the trade-off, really. And so this is very good for storing things that are free form, or storing things where the format changes and the format is not relevant or needed by your application itself, but you just need to be able to store stuff. Or you need a flexible schema. You know, it's good for anything like that. That's why it's called a document database, because every one of these things is just some kind of document, you know, and they're not a particular list of values. They're like anything. So we connect, and then we got a promise back. Sure, whatever. And then you do this. Like, this is very similar to defining the model with Sequelize. Mongoose will let you say Mongoose model, and the model, give it the name of the model, and then you can say what you want your properties to be. And this model will then do all the storing on the back end. Mongo is not going to necessarily guarantee that the schema is there. It might. I'm not sure how much it does these days, but, like, you know, this thing is going to have the schema. And if you change the schema, I'm not really sure what happens.
You can make the schema before you make the.
What do you mean?
With
okay.
I had to learn.
Okay.
I'm still trying to learn.
So this is the model that we're making here.
Yeah.
And then this object is just the schema? Do you set that in MongoDB?
Yeah, you can do like mongoose.schema and then have like basically like the columns of the table.
Oh, cool. Okay.
Yeah. And then that's basically like a row or document, and then the model.
Cool. Okay, so when I get a cat or whatever, it'll be the model, but that will follow the schema. It could follow a schema.
Yeah, it could follow.
Okay. Okay, so that's the, you know, you can say new cat, and these is all from the demo. So you save the kitty, and then how do you load it? Cat dot find.
Oh yeah.
Find. Probably by name. Is that right? Probably a promise. Hey, that's it. So it found the record. So as you can see, like, it's so much easier to get up and running started compared to Sequelize. Like, it's much more intuitive. It's a good tool. The whole thing about, you know, the database and the relational data and everything, it comes into play when you're not doing prototypes. You know, it's going to be a thing, but like, this is a lot quicker to just say, here's the fields and save some data. It doesn't even care what type. Then you didn't even have to say what. Wait, did we say the name was a string? Yeah. Okay. Okay, so you do tell it like what some of the types are, but they're the only types you have are JavaScript types. I don't know, does it have an integer type? Or it's just number type, right? Number. So all numbers are, you know, and I don't know if it, does it have date, or is that part of the browser? New date. No, that works. So you can do dates, you can do probably you probably can't do moment or like a library because it has to be serializable maybe. I'm not sure. I don't know a ton about this. It's a good tool, and Max knows a lot more, and it's probably going to be your friend for some of your prototyping. So again, like your data models are still your data models. You're still going to want your columns, your schema, all of that is translatable and should be used. But you may opt for using this rather than going through all that migration nonsense with Sequelize, because that's what you would do when you're getting paid to do that, like money. You'd put up with that kind of stuff. Anyway, maybe just my thoughts on this, but definitely consider it. Okay. Key value databases are good at looking up one key at a time, very fast from a huge collection of keys. They're not typically designed for range queries. Mongo, you can totally set up indexes on different fields. And it will, I think you can even set up what it calls foreign keys. They didn't used to have that all the time, but eventually they were like, we have foreign keys too. You can totally do, so you totally can try to do like a relational data model in Mongo and set up something called keys. I'm not sure like how well that works or whatever, and it's not, you know, I haven't really seen it at an employer, but there definitely are companies that do it at scale, you know, for real. So I think it's probably viable. It's probably not as common, but you could do a full-on relational setup in Mongo. You absolutely could. It's not as, you know, it doesn't have nearly as good of a reputation for like stability and just sort of, Postgres is like very reliable. So it's one of the most reliable things that has ever been written in terms of software. So it's like, you know, that's the appeal of it a lot, is sort of longer term stability, kind of like, you know, but it's you know, you've seen how much work that kind of thing is. So anyway. Okay. Mongoose is an ODM. It's very similar to an ORM, but instead of relations or tables, you're mapping your JavaScript objects to documents. So that's D, so they call it an ODM. It's like Sequelize for MongoDB. You define the models, which map JavaScript objects to the documents, like we just saw. Mongoose, you know, handles creating unique key, you know, the keys, the actual keys in the database, and doing the actual saving loading. And it works very similar to Sequelize. That's all there is on that. It's actually, you know, there's probably a lot more that Mongoose can do, and I assume, you know, I'm not spending a whole lot of time on it because I assume the docs are going to be much better because it's very popular. But I'm not sure if that's totally true. So schemas, I mean, have you read the docs for this?
Yeah, I just found this is good. Because if you go down to the API,
Yeah.
That's what's really.
Oh man, that's what you want. You shouldn't have to go to the source code for this. That's terrific. You know, that's good. Good docs. Prototype. So this is all, the client has all of these things, right? Model, and so the model API. So you can do count, create, find by ID. And the things on the prototype would be all on when you load something from the database, I believe. Yeah, .save. I don't know. This is Mongoose is the NPM package.
Oh, where is NPM?
Yes, so it's all still in JavaScript. It works. You can do the same exact thing as we did with Sequelize, where you put the calls to Mongoose inside your API. So instead of, you know, doing Sequelize.findAll and then passing that back through Express, you can do, you know, your mongoose model dot find all. It would work exactly the same. And if you want, maybe in the office hours, we could sort of port over the chat app with the 4 endpoints we have to use Mongoose. I don't think it would take very long at all. So I don't want to do that today, though, because we are already in the last hour. Maybe. Does anyone want a break? And then let's talk about a couple more. Or do you want to just plow through? There's not that much more. Yeah. No break. All right. So we can either, yeah. We might have a little bit of time to mess with that then after this. Okay. So that's key value document databases. There are other kinds of databases. Same very basic idea. You write data, you read data. Okay, a queue is sort of one of the first kind of like substantially different patterns for data than a database that we're actually looking at. And this is not something that any of your capstones are going to have to use. But a queue is just like if you just implement it in software. A queue is just like a line, like a queue. You've seen them at the theme park or whatever. The first person into the queue is the first person out of the queue, and everybody lines up behind the first person, and they leave in the same order that they came in. So this is sort of the opposite of a stack. I don't know if you remember stacks from when we were talking about the language. You push onto the stack, and then you pop off the stack. That's like a stack that goes up, and you take the last in is the first out. So that's another word for it is last in, first out, right? A queue is first in, first out. So it's like a stack, but instead of popping off of the top, you'd pull off of the bottom. And then it's exactly the same. And you can do this very, very easily in JavaScript by, you can do this by doing node. Whoops, I'm in my regular terminal. I'm already in Node. Okay, so here's a queue. And it is a const, but we can still mutate it. So we can't reassign queue, but we can push things in and we can pop them out because const really doesn't give you anything that's practical. Anyway, you can do queue dot push something in there. And then if we look at queue, that has one number. Pretty straightforward, right? So let's push in like several more. And if we look at the queue, they're in the order we push them from left to right, right? Pretty makes sense. Now, if we pop, we're going to get 77 because we'll get the last thing we just put in, right? JavaScript has arrays have another method called shift. So you could do queue.shift, and this is going to give you the 1. And then we look at queue, and the 1 is gone. So we do shift, 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 and that's how a queue works. So you could be doing any combination of this. You push and push and then shift and then push. But in every case, when you shift, you're going to get the first thing that was pushed in, not the last thing. And you can do this backwards. You can do what's called unshift, which pushes it onto this side and then pop if you wanted to. You could run it either way. But they'd have to be, if you do shift and unshift, that's sort of like an upside down stack. If you do push and pop, that's a right side up stack. If you do shift and push, that's a queue. And if you do unshift and pop, that's a queue in the other direction. So those are all, that's what a queue means. It's just like a sort of a data structure that follows those rules. First in is the first out. Some queues are not like code in JavaScript, but they're like a queue that you want to be able to connect to. You want many things to be able to connect to the same queue, perhaps, and all add jobs into the queue or add things into the queue or take things off of the front of the queue. So just like a database, there are queues that are running as their own programs that you just connect to and you send data to and you read data from. But in this case, by sending the data, you're pushing into the queue, for example, and by reading, you're shifting off of the front or whatever we call that, right? And there could easily be a stack that's, I don't know if there's actually like a program that works like a stack, or why there would be something like that. It's usually a queue because you're going to use these to sort of distribute and handle surges. So a queue will in front of something will let you easily kind of like handle a great spike in the number of something without any, if you're doing all kinds of database stuff when you get the data and each thing takes so long, if you got a huge spike of stuff, it's going to bog down your whole database because you're doing too many things with each to handle each request. So this is where you take a queue instead, and instead of doing anything with that data right away, you just put it into the queue. Always put it into the queue, and then at the other end of the queue, you have something else running, which is pulling off of the front of the queue and doing your final actual processing with it. And the queue itself then grows longer when there's a big spike of traffic, right? The stuff just piles up in the queue, and then it empties out as it gets processed at the other end. And it all gets processed in the same order than it was sent, so like you get some niceness out of that. But the idea is that it doesn't break. It doesn't just crash or fall over. What's up?
Isn't that what like the pool and stuff is for?
Sort of, but so like each request coming in is sort of in queued, waiting for the next thing in the pool to be available. So yes, your application does have, in some ways, it has its own concept of a queue. There will be in queuing of stuff. But this is sort of like at a larger scale, you might want like a whole bunch of different writers to all go to a whole pool of different processors. You could have 10 things processing data and 1,000 things writing data. And you want it to all kind of like pass through the same process. But each one of those you could connect to one at random maybe, and then just hope it's working. But a queue is like, a nice way to put something there, which is going to handle any kind of spike of surge of extra traffic or whatever. And all it does is hang on to and keep the order that things are waiting to be processed. So it's just a bigger version of exactly what you're saying, the connection pool and the queuing up for a connection, but at a large scale, and it's its own whole program and it's its own whole server, because that's all it does. So yeah.
How is that different from Redis?
Redis can be a queue. So Redis is commonly actually also used as a queue because it's so fast at just writing and reading stuff. And a queue is really just writing and reading from particular places, right? So Redis is very commonly used as a queue. We'll look at that. So worker or workers pull from the other end of the queue. We just talked about that. They don't really talk to the original, the thing that put the thing into the queue. So the one thing you lose is you can't usually respond to the client with the conclusion of all your processing because all you've done is put it into the queue and then it's gone. And the client's like, well, I'm finished. The client is done with its connection, but nothing on that end of the queue knows what happens next. It processed on the far end of the queue. So there's sort of a compromise there for like, you don't necessarily know when it will complete processing, but you know that it's somewhat safe and it's not going to fall over and crash. So yeah. Okay. Yeah, Redis has a lot of kind of like use cases for this, and it has some libraries for queues. Celery is a Python library, which is for in queuing tasks and things to do and then reading them off of the other end, and it scales up very nicely. That's written in Python, and you can use Redis in order to store the data. You can use all kinds of things to store the data. I think you can use Postgres if you want to store the data for the queue as well. But it's more the pattern of how the writes and the reads are happening than it is like a particular implementation of that. PubSub is a very similar pattern. This is like, certain things are writing something in, and then at the other end, something else ends up reading it. It's roughly the same. PubSub stands for publish and subscribe. The difference is when you publish, it could end up going to more than one. So a queue, it's like one thing goes in, one thing comes out, and it gets processed. Publish could be one thing goes in, and it gets sent to 100 people who are subscribed. So anybody who subscribes will receive what it's being published. And you can have different topics, like different, think of it like different magazines or whatever, different people or different processes in the computer are subscribed to different kinds of topics. And everything published on that topic gets sent to everybody subscribed to that topic. So it's sort of like a queue, but it's fan out. It's like everybody who's listening for certain kinds of messages will get a copy of the same message, rather than that message just going to one person at the other end of the queue. Redis has PubSub. Redis does this. It's pretty much built in. The Redis client we just looked at, it not only has get and set, but it has a publish method. I think it has a subscribe method too. So that's basically for broadcasting, an update to a whole lot of subscribers. So if you get like an Amber Alert on your phone or something, or a storm warning or whatever, they're probably using something that resembles a publish subscribe model. And there's all this convention for like push notifications and stuff that goes to phones that's special, but the pattern it follows is very similar. One person publishes a message and it says everybody who's concerned about storm warnings or whatever is a subscriber and will be sent a version of that. And again, Redis is good for that. I'm pretty sure you could wire up Mongo to do that. You could probably, I know Postgres does, like all of these technologies will be able to use for this. And you can rent this kind of thing on Amazon too. Like you can just rent the cloud version of this from, I know I'm saying Amazon, but Amazon has it, Google has it, Microsoft has it. All the cloud people have versions of these, which are just, they have some brand name for it, and you just turn it on, and it does exactly this. Okay, the last thing is streams. So streams kind of combines a lot of these together, and it lets you kind of do like more complicated processing. And this is pretty way out there. This is like what those finance people are using when they process millions of things per second or whatever. A stream system can accumulate huge amounts of data and send it to, fan it out, publish it to people. They call it fan out. You can subscribe to all different kinds of data and aggregate it. That's called fan in. You can queue, you can just enqueue things to be sent along to the next processor in the stream. These systems get very complicated. They're often built around like some kind of logs that just keep a consistent history, and a whole bunch of people append to that log and then read from that log. There's stuff called Kafka, and Amazon has Kinesis, and the other ones have other stuff. But these are basically combine a lot of these concepts and let you do some really ridiculous amounts of processing of data and stuff like that. Okay, don't panic. This is a lot of stuff that you're not going to use in your capstone. It's probably stuff you won't see for a long time because hardly, these are kind of rare unless you go into like a special niche where they've already hired like data people for sure who will be in charge of a lot of this stuff. Unless you go to a company that specializes in this kind of thing, a lot of them will have never even heard of most of this stuff. So they're used for very demanding tasks, usually by people with a lot of experience. They're built into stuff. Like, Redis works as all of these things, or most of them. Postgres works as pretty much all of them. Postgres has internally, it has an append-only log, and it uses that to do all kinds of stuff. they both can be used for pub sub or as queues. There's a Redis client on NPM. I'm pretty sure it has subscribe. Redis client for Node.js. Well, it's comprehensive documentation. Publish, subscribe. Yeah, so you can, oh, okay. So there's like, you do on. So in order to subscribe to a certain topic here, you do on, and then you give it the function for what should happen when any publisher publishes a message on that topic. Everybody who's called this subscribe is going to run this function. And then you publish on topics like this with topic and message, and it's all built into Redis, and it works fine for that. I wonder if Mongo has pub sub with MongoDB. So you can do these patterns with just about everything that we've already talked about. And there's certain, tools that cloud vendors will give you, or certain ones are maybe faster than others, I guess. This is a queue. This is like a very robust distributed queue that uses Redis and is Node. So you use this client, you just tell it enqueue something, and it sends it to Redis, and you say, get the latest thing from the queue, and it gets it from Redis. And you can build a huge system if you want that has a huge queue that all runs with Redis, and it's all NPM installable and stuff. So, it's not like that far-fetched or different from what we've just done today. The tools are all here. A lot of it is more the patterns and what they're called and what you'd use them for, which again is none of your capstones. I think the thing you might want to use for your capstones among all of this is probably Mongoose, if anything. So I'm not, I have a hard time understand. I don't know what I would use. I'd probably start with Mongoose maybe, and then probably build it into SQLize or just build it in Python or something that I like building servers with, but either one will work. The rest of this stuff is just interesting. I don't think anybody's going to have to figure out an index to make any other queries faster. If you're interested in trying it out and seeing which indexes you would make with your data, or try to make a whole bunch of test data, and then see like what how fast it runs and how to make it faster. That's certainly something we can look at. But I think most of this stuff is just kind of like extra information that is about data. It's good to know. It'll probably be relevant. It'll be good to be able to talk about this, in the future. But there's not a whole lot we need to do immediately with any of it. Anyway. That's all for today. What does anybody? Do you want to break early today, or do you want to tinker with the message server? Break early today? Yeah, it's been a long week.
That's a bad question to ask any class on the last day of the week.
Okay. Well, how about this? How about on office hours this weekend? We will do the Mongoose version of the message server. We can do some, just kind of like add some models to that, and we can try some indexes if anybody wants, or we can just do Bootstrap, I don't really mind if you want to break from all the data stuff or whatever. So we'll say Sunday. Does anyone have a preference for time, afternoon?
Sundays are another holiday.
I think the holidays are.
I don't think there's my holiday until the 4th, so 2 weeks from today would be the next holiday. term
Fourth of
today is
July.
4th of July.
We have that day off.
You do? Yeah, I'll still be going.
You get-
Speaking of which, I don't think over here on Monday. They
Okay.
teach you next week.
No, Max will be back next week. He's gonna go into more sort of like fully utilized servers. So you're gonna continue building servers to serve your API data. We'll still be working with data, officially in homework and skills to get your data models. But, I'm flexible on.
So when you say,
Data for that.
when you say you're building servers, you basically mean you're formatting the server.
Yeah, well,
What does that mean when you say
something,
you're
as
building?
much as you think you're gonna get.
Writing the code.
Like creating a database.
But you're
Not the
creating,
database though.
there's the hardware, and you're like telling it how you want it formatted, is that right?
Sort of. I mean, the server does things like, it obviously, yes, it formats and loads and saves from the database.
I mean,
But
the server is a thing, right?
a server is what I'm using is a program that's running.
Okay,
My
so you're
laptop
talking
is,
about
my laptop has the database, it has the server, it has the client. All of those things are just programs I'm running. When you do it for real, you would deploy your application onto a virtual, it's actually not a physical box anymore, it's a virtual.
But then as soon as I'm busy, they're like.
It might as well be a physical box.
Do you know
Probably
that
a cloud provider that say run the server. And it runs in one place, and then you run your database on another hardware ultimately somewhere.
I mean, I understood that, but you guys use, I just want to make sure that the language you're using is the way I'm understanding.
Yeah, so the database is a kind of server, the Redis is a kind, but when I say server, I usually mean the API server. So your custom server, which uses Express or whatever, and it has the endpoints, the REST endpoints to like say, to access the data that your application. So that's, it's sort of the way, yes,
Another question about the blockchain thing.
yes.
So I'm just curious about this, because when, a couple of weeks ago, Huawei was a big story, so I asked Max about it.
Yeah,
So he basically said, well, Huawei, that's great, but they could build a back door into anything and you couldn't detect it. That's what I read. And he's like, yeah, they could, and you wouldn't know, and blah, blah, or maybe I just read that, maybe Max didn't say it, but whatever.
yeah.
So now Doug is talking about the contracts from these people in Buenos Aires, right? Couldn't they be building a back door into all those contracts so that they could have?
I mean,
I'm not saying they are, I don't know anything about them,
it's
but
probably
isn't it possible?
harder, it's probably harder to hide such a thing if you're building it into an open source distributed piece of software.
Right.
Because anybody could look at that software and notice.
No, I'll be back.
Notice
That'll be online if you have.
the tricks or whatever
Right.
you've added to it. It's,
But you can't do that with.
Sounds good.
well, Huawei gives you basically a hardware box.
Uh-huh,
And they don't publish their source code for that on the internet. And they just give you this box, and you would have to open that up, and they do, obviously. I mean, I'm certain researchers,
Right.
security people, they open up the box, and then they sort of put special leads and clips and things,
right,
and crack the chip open and read the
Right.
memory. And then you have to sort of decompile it, so it's all in binary machine code format.
right.
You have to uncompile it into like a language that
Uh-huh.
actually looks like something. And then you have to look for the bugs. So there's a whole lot more involved.
Because the intelligence agencies have all done that,
Well,
and they're always
It's
like
a lot of work.
inconclusive.
it's a lot of work, and that is true. I mean, if they had found something for sure, they haven't told anybody about it. They're
Right.
either
Seems like they would
holding it
tell
as a
us, yeah.
negotiating card, or they've not found anything. Yeah.
Well, I don't think they would. I mean, I'm just trying to, I'm more like just a nerd about like government and.
Yeah,
who's telling the
geopolitics
truth.
and finance and bitcoins.
I don't particularly
Anyway, on that
feel,
note,
I'm not a very trusting person, I suppose.
have a good evening. Thank you for tuning in.
Thank you for
so long.
indulging me, my suspicious nature.
Hey, that